So in this function, we have a rational function because if you notice, my numerator and my denominator are both polynomials. So I'm going to go ahead and spend a bunch of time just finding all of that information from our half sheet notes from this function. So for starters, what I'm going to do is figure out the domain. For me to find my domain, I have to make sure everything is in factored form. So I'm going to factor the numerator, x plus 3, it's already factored. And then I will factor the denominator. So however you like to factor, I usually guess and check when I factor. So let's see, I need an x, I need an x. Looks like a minus 3 and a plus 1. There you go. So this is my factored version of my equation. You'll notice I don't have any factors in common, like x plus 3, x minus 3, x plus 1. None of them are in common. So nothing's going to reduce out. But before I even think about that, I'm going to figure out what my domain is. So my domain, as we talked about from before, you can't divide by 0. When we have this going on in my denominator, there's two restrictions on my domain. Either x plus 1 can't equal to 0, or x minus 3 can't equal to 0. So that means x can't equal to -1 and x cannot equal to 3. So if I were to write my domain, it's easiest to write it in set notation because there's more values that your x can be versus can't. So there's only two numbers that don't work. And I'll say it can't be -1 and it can't be +3. So that's my domain. Now, the next thing I'm going to find is the reduced form of my equation. So my reduced form is actually already like what this problem said when I factored it. This is my reduced equation, okay? Because there's really nothing that I can factor out. So I'll say already reduced. Our third thing is talking about if there's any holes. Now, the holes really come from whether or not you can take out any factors, but since I didn't cancel out any factors, there's no holes. So I'll say no holes since we didn't cancel out any factors. So that's actually kind of good. That means I won't have any random open dots on my graph. Now, the fourth thing that we're going to find So our fourth item from our half sheet is all about the y-intercept. So to find the y-intercept, as you recall, it's going to be something comma a number, so 0 comma y. So I'm going to write y-intercept. For me to find the y-intercept, we're just going to substitute x equals 0 and figure out what happens. You put it in the original function or you can write it in the factored version. I usually like to use the factored version. I don't really know why. So I'll say r of 0 equals, I'll say 0 plus 3 all over 0 plus 1, 0 minus 3. On the numerator, I'll get 3. Denominator, I'll get 1 times -3. So it looks like my y-intercept is going to be at 0 comma -1. So I'm going to write that down. I'm going to box it as well so I know that this is something that eventually I'm going to be able to graph. Next thing I ask you to find is x-intercepts. Now, x-intercepts are when you look for when r of x equals 0, like you're setting your equation equal to 0. Let me kind of show you why that shortcut I was talking about earlier works. So our function x plus 3 over x plus 1 x minus 3 if I set this equal to 0. Some people get freaked out because it's like, oh man, I got this fraction equal to 0. But truthfully, what we usually do is to try to get rid of that denominator by multiplying it on both sides. So I'll multiply by x minus 1 and, or I'm sorry, x plus 1 and x minus 3 onto both sides. When I do that, you'll notice on the left-hand side, like these factors will cancel out. That was kind of the point. I wanted to get rid of the fraction, so what's left over is just x plus 3. But on the right-hand side, since I'm doing 0 times x plus 1 and times x minus 3, doesn't that still just give you 0? So the shortcut, again, was just to set your numerator equal to 0. That is a nice shortcut because when you're looking at a rational function, this situation will always happen. So now I'll just solve this equation for x. I get x equals negative 3. Again, for my own ease, that means negative 3 comma 0 is an x-intercept. I only have 1 in this case, and that is the 1. Let's move on to item number 6. Item number 6 is finding the asymptotes. So there are several asymptotes I have to think about. First, I'm going to think about vertical asymptotes, and then I'm going to think about if it has a horizontal or oblique asymptote. So I'm going to look back at this little flow chart that we have. I'm going to write number 6. Vertical asymptotes are going to be first. So you're going to set the denominator of r of x in lowest terms equal to 0. You'll notice I kind of did that for the domain. It's going to feel the same here. My vertical asymptotes come from, because this has no reducing things that I can reduce out, I'll have one vertical asymptote at x equals negative 1. So I'm setting my factors in my denominator equal to 0. So here's a vertical asymptote, and here's another vertical asymptote. In addition to finding vertical asymptotes, I'm going to have to look at if it has a horizontal or an oblique asymptote. You can't ever have both in the situations that we're talking about in this unit. So let's talk about which kind of branch it's under. So it says degree of the numerator, degree of the denominator. You can look back here at my factored format, or you can look at the original. Doesn't matter. But it looks like the degree of my numerator equals 1. Right? The degree of my denominator, again, if I multiply this out, or even if you look at the original multiplied out version, is 2. So I know I'm not looking at this middle branch because my degrees are not the same. So I'm going to cross that out. I'm also not looking at this last branch, because my degree of my numerator isn't bigger than the degree of my denominator. So I'm going to cross this out as well. Since 1 is less than 2, I'm looking at this branch. AKA, it's just telling you you've got a horizontal asymptote, and it is at y equals 0. I didn't actually have to solve anything for this one. Last but not least, this is cross points. This is going to feel the weirdest because if you have a cross point, truly that means like your graph is crossing through an asymptote. I don't think you've ever seen anything like that happen before. So I'm going to write down 7 is cross points. So for me to figure out if I have a cross point, I'm going to take my answer from number 6, aka my horizontal asymptote, which is y equals 0, and I'm essentially going to solve like a system with my horizontal asymptote and then with my function, which was x plus 3. I'll use the factored version again, x plus 1, x minus 3. So I'll just say r of x. So when you're solving this system, because they both equal to y, you can do a little substitution, right? Since they both equal y, that means the two have to equal each other. So you'll say x plus 3 over x plus 1 times x minus 3 equals 0. Will this ever have an answer? This might feel familiar because we actually just solved an equation like this. So I'm going to get the denominator out here by multiplying both sides by this. This will cancel out over here. This turns into 0, and I actually do get an answer here. X equals negative 3, right? A lot of people wonder, like, what is my y value in this situation? Because a cross point should truly have like an x comma y. In this case, we just figured out the x coordinate is negative 3. The y coordinate is actually just 0. because of the way we had set it up. Or you can substitute in -3 into my function. You'll notice I'll also get 0 if I do it like this. All right, so my numerator, I'm going to get 0. Denominator, I'll get -2 times -6, but 0 divided by 12 is still 0. So if I asked you if there are any cross points, this one has a cross point at -3, 0. So that was our first stab at figuring out all the information for this rational function. Eventually, you're going to put it all together on a graph and kind of connect things to see what it will look like.